Okay, in the last class, we have discussed about this nuclear fission process and fission reactors. In today's class, we will discuss about the nuclear fusion process. Okay, so nuclear fusion process, and after that, nuclear fission reactors and fusion process, which is happening in sun and other stars. Okay, so let's start with this topic, nuclear fusion. This is a very familiar topic which you might have learned from your high school itself. So this is nothing but the two lighter nuclei combined together and form a heavier nuclei with release of energy. Okay, so that is nuclear fusion reaction. So that we can get from that binding energy per nucleon curve also. You might have observed that the binding energy per nucleon curve, which is almost like this. So I will just write here. This is your binding energy per nucleon, and this is your mass number. Okay, so that will be having some kind of average shape like this, smallly increasing. So if you consider any the nuclei in this range, okay, mass of the nuclei, and we already discussed about the fission reaction. So the whole the nuclei which are coming at the end of this binding energy per nucleon curve, which are having binding energy per nucleon which is less, and they're having very large mass number, heavy nuclear size. So that nuclei, such kind of nuclei will divide, or they will split into two, and that will form nuclear fission process, and the which results in two daughter nuclei which may be having same size, but the probability is higher for uh, having mass number different mass number. So the daughter nuclei will be having, normally nuclei will be in somewhere here. So their binding energy per nucleon shift is somewhere here, which means that the binding energy per nucleon will be increased. So the nucleus will become more stable. So that is the fission process. Okay, heavier nucleus splits into two lighter nuclei. In this case, two lighter nuclei, suppose somewhere here, if there are two lighter nuclei which are having binding energy per nucleon which are smaller, they combine together and they can go into the higher binding energy per nucleon regime. Okay, that is called as fusion reaction. In this particular case, two lighter nuclei combine together, form heavier nuclei with release of energy. That is your nuclear fusion process. So I will just write here two lighter nuclei. Or you can say that two nuclei having mass number, very small mass number. Normally, it is lighter nuclei, very lighter nuclei, which participate in fusion reaction. Okay, so this lighter nuclei combines together, combines to form heavier nuclei, which having more binding energy per nucleon value. Okay, and along with release of energy. So this process, we'll put some comma here, value, energy value. Okay, so this is called as nuclear fusion. This is not the right definition. I'm just writing it. You can say it like this. Okay, so this is the nuclear fusion reaction. Okay, for this particular case, let's consider an example. This example, let's consider neon. This is neon 2010 plus another same nucleus, which is combined to form, let's say, calcium 40 and some photons. So this is a fusion reaction. If you want to find out the energy which is released in this fusion reaction, so there will be some energy which we normally represent as Q. Q value of this reaction, which is nothing but the energy released in this particular process. So that Q value will be given by the energy of this um, what we call as reactants, or what we can say that the lighter nuclei, hmm, that has to be subtracted from the energy of product nuclei. So that is mass of this part, that is neon in this case, in this time. So two neon nuclei are present. So 2 times mass of neon times c square will come. Okay, so it is nothing but 2 times that will be multiplied with this mass of neon 20 times c square. Okay, so this is the energy associated, total energy associated with that nucleus, neon nucleus. So there are 2 nuclei. Okay, so that's why I put 2, and this has to be subtracted from mass of calcium 40 nucleus, that has to be multiplied with the c square. So again, 2 times, what is this value? So this will be, I will just put some curly bracket here. So this is 2 times 10 times mass of neutron plus 10 times mass of proton, that 10 number of Z and 10 number of neutrons will be there. So this is total mass, same, into c square. This has to be decreased, this has to be taken subtracted from that binding energy. So that is in this particular case it will be mass number is 20. So 20 times binding energy per nucleon of 20 neo. Okay, you don't have to confuse with this, because we have a total energy this much, 10 number of neutrons per mass of neutron, that is 10 times mass of neutron plus 10 number of protons, so that will give you 10 times mass of proton, that is the total mass, into c square is the total energy of the nucleus. That has to be subtracted from the binding energy of nucleus, then you will get the energy of the nucleus that is available. Okay, so total energy minus binding energy is the energy of that nucleus, available energy of for that nucleus. So that will be minus 20 binding energy per nucleus. So this A will be mass number. So this is nothing but 20. So 20 20 will get cancelled. So this is nothing but the binding energy. So your total energy is subtracted from this binding energy, and what is that result will be the energy of that nucleus. And this has to be I think, okay, so that 2 will be multiplied with this, and this has to be subtracted from that 20 times mass of proton plus 20 times mass of neutron times c square, that is the energy, uh, total energy for the calcium, and that has to be again subtracted from 40 times binding energy per nucleon of calcium 40. So when you consider this, you can see this 2 times 10 mass of neutron times 10 mass of proton, this into c square, that is available here. These are same. Okay, because 20 mass of proton in plus 20 mass of neutron into c square will be equal to 2 times 10 mass of neutron plus 10 mass of proton into c square. So these terms will get cancelled. Only that remaining 40 terms will be there. That is uh, 2 times minus 20, so minus 40 times binding energy per nucleon of neon. Okay, minus minus. So this will become plus 40 times binding energy per nucleon of calcium. I will write 40 outside, okay, and then I will write positive term first. So binding energy per nucleon of calcium 40 minus binding energy per nucleon of neon 20. So this is the Q value or Q energy which is released. So this is if you substitute those binding energy of neon and binding energy of per nucleon of that calcium, and that has to be multiplied with this 40. You do all those things, then you will get 23, almost 23 mega electron volt. So that is the energy released in this particular nuclear fusion process. Okay. So now, if you consider this particular nuclear fusion reaction, it has a lot of advantages compared to the nuclear fission reaction, because when you have that fission reaction, that doctor nuclei were subsequently again going through those beta decays. Okay, so several beta decay process happens. So it is radiation hazard for nuclear fission process, which is larger. Radiations are much radiations nuclear particles are produced in case of nuclear fission process. So radiation hazard is larger in case of nuclear fission process as compared to nuclear fusion process. Similarly, if you consider the stability, nuclear fission process, we discussed about the critical, subcritical, supercritical situations, and making those fission reaction in a comfortable way, in more stable way, which is very crucial. So that stability, in terms of that stability, nuclear fusion reaction is more uh, stable as compared to the nuclear fission process. Okay, and another important point is that if you study the nuclear fusion, then you can also study the different processes which are going through the core region of the sun. Okay, or any other the stars. Okay, the same fusion reaction is also happening in there. So once you have these nuclear fusion reactors, and if you can study this nuclear fusion process under different circumstances, different conditions, physical parameters, all those things, then we can have some better idea about what is happening in that core region of the sun and other stars, all those things. So it is nothing but a modeling of sun or other astro physical bodies, okay, heavy bodies. So that can be studied. That is another advantage of studying this nuclear fusion process. But we didn't have this nuclear reactor. We still don't have that. It is still under developing because of some factors. We cannot yet. We are not able to build that nuclear fusion reactor. So what are these barriers or the limitations that we are having to build these nuclear reactors that we will discuss now? Suppose two nuclei, lighter nuclei, combining together through that nuclear fusion process. Let's say this is the first nucleus and this is the second one, and these nuclei are combining together to form a heavier nuclei. Okay, some plus gamma radiation, all those things will be there. So let's take this separation of this nuclei initially, which is I will take this as R, and I will take this as capital R, this radius capital R, and this is not that much required, or I can write R1 here. This is R2. So if they are same, then they have same radius. So I will just put this as capital R1 here. This is capital R2. So I'm considering they are having some differences in their size. Hmm. So these two nuclei with R1 and R2 are the radius are combining together to form another nucleus of having radius capital R. Okay, and the separation between these initial lighter nuclei, okay, this separation is nothing but small r, and if you draw that small r versus potential curve, so initially if these two lighter nuclei which are very far away, then this nuclei which are positive, okay, if you consider that charge of this nuclei, it is positive. Okay, so when they are very far away, they are not dependent on each other, but when they come closer and closer, then the Coulombic repulsive force will come to picture, because they are having positive charges. When two positive charges come closer and closer, there will be Coulombic repulsive force and Coulombic repulsive potential associated with that force. Okay, so when the r is at very large distance, so there is no interaction, or the interaction is very small, but when the r is reduced, it will appear that the Coulombic repulsive force will appear, that associated with that, because of the force is repulsive, we have potential which is positive. So that potential energy will be like this. So then when r is larger, it is having some potential energy like this. Then when you make these two lighter nuclei close each other again and again, which are coming closer and closer like this, so that Coulombic potential repulsive force and potential will increase when they come close to each other, which means that r is decreasing. Then suddenly, when it is very close enough to have that nuclear fusion process, which means that they are in the range of that nuclear fusion cross section, which means that when this first nuclei approaches to the second nuclei, it has to be in some distance, very small distance, very close to each other. When then only you can have that nuclear fusion process. Okay, then only they will combine together. So they have to come very close to each other, and how much they have to come, that is decided by that fusion cross section. Okay, so if you consider that particular case, then at that time when they are very close to each other, that fusion will happen, and suddenly this potential will come to this point. And if you make it further, and that will be nothing but the uh, attractive potential, nuclear attractive potential of this product nucleus. So this suddenly goes down like this, almost like this. So here we have something like this kind of shape, and this is it will be almost like this. So on this side, it is having that 1 by r form, that is the Coulombic repulsive form. So you draw it like that, and here we have that maximum potential, and this maximum potential will be, let's say it is V0. I will put it here also. So this is your V0. That maximum potential will be the atomic number of those lighter nuclei times E square. That is the total charge, okay, inside that nucleus. That is the protons that we are considering. and then that is divided by 4 pi epsilon 0 times what is the first radius is r1 plus r2. So this is maximum potential that you can have, because when r1 plus r2 is minimum, you can have that maximum potential. They are very close to each other. So that is the maximum potential that is available. So in order to have that nuclear fusion reaction, you need this much of energy, minimum this much of energy that is required in order to cross this potential barrier. And this barrier is, uh, as you know, this is coming from here, this side. Okay, so this potential barrier is having height, this much of height, that is v0, which is given by that Coulombic repulsive force. Okay, so here the barrier is formed because of that Coulombic repulsive force, and because of that Coulombic repulsive potential, then you have to apply minimum energy required to cross that particular potential, this particular potential barrier. Then only it can reach in this uh, fusion stage. Okay, then only it will fuse. Suppose you are having energy which can reach up to here, but it will not come to this end because it still need this much of energy to cross this barrier. Okay, so it need at least that barrier height, that energy, potential energy, which is coming from that Coulombic repulsive force. So because of this potential barrier, normally all those lighter nuclei will not go and combine together to form this fusion. That is not going to happen. So the potential barrier which is there because of the Coulombic repulsive force, that is one factor which limits the fusion reaction. Okay, so that lighter nuclei should have at least some energy to cross this barrier. Hmm. For if you consider this for the case of the neon-neon fusion reaction that we just discussed, so this value will be somewhere around some 20, around some 20 mega electron volt. This will be 20 mega electron volt. So you need at least this much of energy for your nuclei, lighter nuclei, which are combining together. Okay, so at least this much of energy is required to cross that potential. Otherwise, they will not come very close to each other because of that Coulombic repulsive force. So when they have that Coulombic repulsive force, you have to apply some energy to overcome that Coulombic repulsive force when they come very close to each other. In other words, you have to overcome this potential barrier formed by this Coulombic interaction. Then only they can come to that fusion cross-section range and combine together to form these heavier nuclei. Okay, so that is the first limitation. But if you analyze this, if you reduce this z1 and z2, you can reduce this v0, right? Because z1 and z2 in the numerator. So if you are having very light nuclei, so then this barrier will be having very small value. That is obvious. So when you consider the proton-proton interaction, let's say proton interaction. What is this proton-proton? You know this H1 interaction. So in this case, your Z1 is very small. Only one proton you are having. So you have a 1 into 1 here. Previously you are having this 20, sorry, this is 10 times 10. So this itself will give you 100 times. Okay, so in this case, when you are having this proton-proton configuration, Z1 is 1 and Z2 is also 1. So this is simply 1, only E square by 4 pi epsilon 0 will come. Okay, and also for H1, it is radius is also which is very small, but In this particular case, you have to consider that R1 plus R2. So anyway, so because of this action, when your Z1 and Z2 are very small, your V0 will be small. For this particular case, we have that V0 which will be in that kilo electron volt range. So if you calculate this, it will be somewhere around 720 kilo electron volt or something in that range. So this lighter nuclei, they will be having very low potential barrier to cross, because they are having proton number which is smaller. So the proton repulsion will be smaller. So the Coulombic repulsive barrier, potential barrier will be smaller for lighter nuclei. So we have to choose some very light nuclei to have this nuclear fusion reaction. Or in such nuclei where you have the mass number or the proton number is very small, then you can have the nuclear fusion by applying some small energy compared to the heavier nucleus. Okay, heavier nuclei. In this case, we have taken neon. It is having 20 mega electron volt range. But when you consider that proton-proton interaction, then it is only 720 kilo electron volt. Okay, so the energy is reduced. Potential barrier energy is reduced. So only this much of energy has to be provided to cross that potential barrier. Okay. Now, if you consider any isotope of these elements, they will be having further that radius will be increased if you consider isotopes of this nucleus. So that will leads to increasing the radius of those nucleus. Then that uh, means if you consider any isotope of this, so what will happen for these isotopes? Let's say like deuteron. Let's check that spelling. So deuteron, we have H2. So one proton, one neutron, that will make that deuteron, and that deuteron will be having same number of proton with these protons. Number of protons will be same in this proton and this deuteron, but this will be having higher size, which means that higher radius. Nucleus will be having more radius here as compared to this. This is having only one proton. This is having one proton and neutron. So the nuclear size will be larger here, which means that R1, R2 value will be larger here. So this will further reduce this potential barrier. Okay. So that also you keep it in mind. So when you use any isotopes of these with the same proton number, but mass number is different, like deuteron or triton with H3. Okay, so this will increase their size because mass number is larger. It will increase their size, but it will not increase their number of protons. Number of protons or charge will be the same. Uh, uh, Such kind of isotopes I'm saying. So for that example is deuteron. So in that case, deuteron, which is having same number of proton but different number of mass number, which means that different in size. So such nuclei will be having more radius. For in this case, deuteron will be having more radius, so that R1 plus R2 term in this potential barrier here, that will be larger, which means that this V0 further goes down for isotopes of this. So this can be again reduced by using those isotopes. So in order to have this nuclear fusion reaction, we need this much of energy, which can cross this potential barrier, which can be done by using some accelerators. But the energy produced in this fusion reaction will be much lower than whatever energy we have to provide for the nuclear fusion to happen. Okay, so whatever we discussed so far is we require some energy to cross this potential barrier. Okay, so here we need some minimum to cross this potential barrier. Okay, so this can be achieved by acceleration, accelerating the lighter nuclei. Okay, that can be done through that acceleration. The energy of those reactants in this nuclear fission process, that can be increased. Sending those lighter nuclei through some accelerators, and when these accelerators are working under some principle and providing some energy to those lighter nuclei, their kinetic energy will get increased, so that that energy can be used to cross this potential barrier. Okay, so when they are accelerated, their kinetic energy will get increased. Suddenly, if they are coming close each close enough, then this nuclear fusion can be possible if those nuclei are having energy which can cross this potential barrier. Okay, so in accelerators we can increase the energy of these nuclei, lighter nuclei, and when they are having enough energy, if they are coming very close to each other, they can combine each other and form this fusion reaction, because that accelerator provides enough energy to cross this potential barrier. That can be possible, but the problem is that if you are having such kind of accelerators, the accelerators will be working with different components, different heavy parts, which has to be working under some physical laws and different mechanisms, machines, all those things will be a part of those accelerators. Then it requires more energy to accelerate that particles inside. It require energy. Okay, so that accelerator will be having different parts, different machines, different electronics components, all those things, and different physical mechanisms to operate with. So all those things we have to consider, and all these things will be working uh, uh, with some energy from somewhere. Okay, so that energy required to accelerate the particles, that energy must be less than the energy produced in the nuclear fusion process. Then only we can get some energy gain in this process. Okay, if you are providing this lighter nuclei, if you are providing energy through some accelerators, and if these accelerators are used energy which is much higher than that of energy which is released in the fusion reaction, then it is a loss. Okay, that is not a good idea. The fusion reaction, once it happens, it will produce some energy, it will give some energy through that reaction. That energy must be higher than the energy used to accelerate those particles. Then only we can have some gain in energy. Okay, so that is one limitation that we have to consider. Even though if you are accelerating those lighter nuclei, still, if those nuclei are fusing and producing energy, if that energy is coming less than what the energy required to accelerate those lighter nuclei, then it is not going to work. Okay. Another possibility is that, so first possibility is through this accelerating, but if that accelerator requires more energy, then this energy which is released from this fusion reaction, then it becomes a loss, and that idea will not work out. And then we have to look for another idea. So that is another possibility is through making these nuclei in a plasma state. Okay, so when it is in the plasma state, the temperature can increase their kinetic energy, and which can be able to uh, penetrate the potential barrier, and such reactions are called as thermonuclear fusion reaction. Okay, so in here what we are going to do, another possibility another possibility is that another possibility is through the uh, making the nuclei in into plasma state. Okay, so that plasma state is nothing but electron, that the nucleus, in this particular case, this nucleus and electrons are separated from that atom. Electrons and nucleus are separated. That is that plasma state. So if you make a plasma state of those lighter nuclei, the temperature can, I will write it here, then the temperature can increase uh, increase the kinetic energy of those nuclei. Okay, and which can get enough energy to cross the potential barrier and fission take place. Okay, so this is another idea, not that we discussed that. So this is another idea. So what will happen in this particular case? We make a plasma state of those lighter nuclei, reactant nuclei, and then we will increase the temperature little bit, so that the temperature, increasing that temperature will be enough to provide some kinetic energy for those nuclei, and that can break those potential barrier. It can break through this potential barrier and fusion take place. But when you consider that what kind of temperature requires in order to do this, for example, if you consider the room temperature, at room temperature, what will be the energy? So room temperature means 300 Kelvin, means 27 degrees Celsius. So Kt is the energy. Kt will be equal to 0.027 electron volt. So average energy, if you consider, average energy is nothing but 3 by 2 Kt. This is 1.5 times 0.027 electron volt. Okay, so this is very small, very small as compared to that mega electron or kilo electron volt range. We calculated that even for that proton proton interaction, we require minimum some hundreds of kilo electron volt energy. Okay, but here we have only electron volt energy at room temperature. So at room temperature we cannot expect this plasma state. In that plasma state it can go for fusion reaction, because that potential barrier still is very large, which is very large as compared to this energy. So at room temperature it will not happen. Okay, so this is average kinetic energy, 3 by 2 kt. I hope you know this. If you take each dimension, you have 1 by 2 kt as average. For 3 dimension, you will be having 3 by 2 kt of average energy for those nuclei. Okay, so this is the room temperature energy, and that is kt at kt at room temperature at this much of temperature, that will be 0.027 electron. So this is very small energy at room temperature. So when we consider the temperature, we look in a different angle. So what should be that temperature? What should be the temperature? Okay, that is required to cross that potential barrier. So we assume that the average energy, if it is crossing that potential barrier, then that 3 by 2 kt will be let's say some 150 kilo electron volt. Just an assumption, 150, some kilo electron volt range of energy we require. So let's say that the average kinetic energy which is given by this temperature in that plasma state, which is 150 kilo electron volt. So that temperature will be nothing but, this temperature will be now 2 by 3 times 1 by k times 150 kilo electron volt. So if you calculate this value, 3 by 2 is almost 1.5. You can take it like that also. So this is some 100. I have taken this 150 in order to make this calculation easy. So this is somewhere it is 150, so 1.5, then it will become 10. Okay, sorry, 100, 1.5, it will be 100. So then 100 divided by this Boltzmann's constant, that is 8.6 into 10 to the power minus 5 electron volt per Kelvin. Okay, electron volt per Kelvin. And this is 100, what is that, kilo electron volt. Now, if you do this calculation, then it will come around 10 raised to 9, order of 10 raised to 9 Kelvin. Okay, this much of temperature required. So this is very, very huge. It is very high temperature. Require that 10 raised to 9 means that is 10, and then you have that 8 zeros, all those things. So it is almost 10 to the power 9 Kelvin. It is very high temperature required to have that kinetic energy, average kinetic energy of 150 kilo electron volt. What it means that your daughter nuclei, sorry, your reactor nuclei, that should be having this much of temperature, 10 raised to 9 Kelvin, in that plasma state, then only you can have a 150 kilo electron volt of energy. Then if that potential barrier is coming below this 150 kilo electron volt energy, then only that fusion reaction will happen. Now, if you consider in the case of sun, okay, so we know that the sun is having this nuclear fusion reaction, which is happening inside this core of the sun. So there is no nuclear reactors, fusion reactors are not there. There is no humans to work all those things. All those things are happening inside the core. So how it is happening? So from that we understood that for the core of the sun will be having a temperature of 10 to the power 7 Kelvin, of the order of 10 raised to 7 Kelvin of water. And if you substitute this value in that 3 by 2 kT, 3 by 2 kT, that will give you almost 1 kilo electron volt. It is still low. Even if you consider the core of the sun, the temperature is 10 raised to 7 Kelvin, and if you calculate that average kinetic energy of those lighter nuclei inside that core, still it is 1 kilo electron volt of kinetic energy for those lighter nuclei inside sun. Still it is not possible to break that potential barrier, but still it is happening inside the sun. How it is happening? It is happening because of the concentration. Okay, so in sun it is happening because along with this high temperature, there is this lighter nuclei, whether it is proton, neutron, triton, all those things, which are in abundance in the core of sun, which are very dense. Okay, so due to this dense or concentration of those nuclei, which are the reactants of this nuclear fusion reaction, that produce the nuclear fusion in sun. Okay, so still if you consider this 10 raised to 7 Kelvin, if you consider that what is that, Maxwell's, from here we can say that first. From here we understood that 10 raised to 7 Kelvin, and it is having 3 by 2 kT, and which is 1 kilo electron volt. If you substitute this 10 raised to 7 Kelvin in this expression, okay, but all those nuclei will not be having this much of energy. Some nuclei will be having more energy than this, and that can be observed from that Maxwell distribution, tail of that Maxwell distribution. So if you consider the number of particles with velocity v in between v and v plus dv, this is what we are representing is that the number of particles with velocity between v and v plus dv. So that is given by that Maxwell's distribution. Maxwell distribution, that is nothing but 2 by pi. I don't know whether you're familiar with this, but it is 2 by pi 1 by 2, that is root of 2 by pi m by kt all raised to 3 by 2, and this times k square, sorry, this is v square times e raised to minus half mv square by kt. So this is all in that exponential. And from here we can, if you draw this distribution, you will get something like this. If you draw this distribution, then it will be almost like, so it will be going like this and increasing, and there will be having a small shift in this region, and then it is decreasing. There will be a small shift in here. It will be a little shifted like structure, and then it is decreasing. So it will be going like this. So it is not going to become zero here. Almost, it will be almost zero. I will redraw this again. So it will be small shift here. So it will be going like this. So when you consider this tail portion of this distribution, what I mean by tail portion is this side. Okay. So we can see this is number of particles with that velocity v, and this is the energy. In other words, we can say that is v. Half mv square is the energy. So it is also proportional to that energy. So with large, almost the average, if you consider it will come here. That is the average speed or average velocity. So that will be here in this point. So that is maximum number of particles are having this much of velocity. That is the average velocity, and that is given by this 3 by 2 kT also. That energy associated with this much of velocity. But if you consider this tail, which are having more velocity, those nuclei or particle are having velocity which is much higher than this average velocity. So that those particles will be having more energy, okay, which are coming in this tail portion of those. But the number, if you consider that number, it will be very small. If you consider that number of nuclei or particle with higher velocity or higher kinetic energy, that will be small. That number will be small, but still there will be some nuclei, some particle. If you consider that Maxwell distribution, in this particular case, it is that some nuclei will be there with enough energy to cross that potential barrier. But most of the nuclei, almost 99 percentage of the nuclei will be having lesser kinetic energy than the potential barrier, but very few number of nuclei will be having enough energy to cross that potential barrier. That we can get from this Maxwell's distribution. And if you consider that probability of that fusion reaction, if you consider, and that probability will be almost zero in here. Okay, all this region will have that zero probability because that energy is very small. So when that velocity is small or the energy is small, there is no probability at all. So that will be here. And then when it is going to that tail of that Maxwell distribution, it is suddenly, it is gradually increasing. So it is very small here. So the probability get a little higher. So probability slightly increases when it goes to that tail of that Maxwell distribution. So those nuclei which are having some higher energy than the potential barrier, some number of nuclei will be there. And associated with those number of nuclei, the probability, there are slightly some probability for the fusion. Okay, so this green color is probability. I should say that nuclear fusion probability. So because of high energy in the tail portion, there it can possible. So the probability is higher. So that will just start to rise. So still the probability is very small, but it can be possible for very few number of nuclei that can cross that potential barrier and fusion reaction can occur. Hmm? So that is about this nuclear fusion happening in sun, but it also depends on that density. The density also depends on this in the case of sun. So that also we have to consider. So this probability of fusion also depends on that the reaction rate of that nuclear fusion is depends on the concentration or density. It also depends on the temperature, because when you have more temperature, you are having more kinetic energy. So it depends on the temperature. Okay. Also, it depends on the cross section of fusion that already we discussed. And it also depends on the relative velocity of those nuclei, initial nuclei. All these things which is related for this nuclear fusion. So I will list here that those nuclear fusion which are depend nuclear fusion reaction, I'm saying. The nuclear fusion this reaction, this is depends on that temperature, and it also depends on that density of those reactant nuclei. Then we have the fusion cross section. Then it also depends on that relative velocity of those nuclei. Relative velocity, because if the velocity is larger, you'll get more energy. So, and also because of that random motion, the velocity of those nuclei which are interacting, combining together, also uh, have some dependence on this nuclear fusion process. Okay. Now, if you consider all these into account and write that rate of the reaction, rate of nuclear fusion reaction, if you write, then it is R equal to some constant times nx times ny times sigma v, that is the average value of the sigma v. So here nx, nx is nothing but the concentration or density, concentration of x nuclei, nucleus I will say, and this is the, and y is the concentration of y nucleus, and then you have that sigma, that is nothing but the cross section, and the cross section what we are saying now is that fusion cross section. Then we have that v, that that average velocity. So that rate of reaction, which means that how many reactions will occur, how many nuclear fusion reaction will occur per second. That is that rate of reaction. That will be proportional to the density of those reactants, that is Nx and Ny, and which also proportional to that nuclear fusion cross section, and it also proportional to that relative or the average velocity. So we have to take average of this velocity as well as cross section, because this cross section also a function of velocity. So that's why we have to take the cross section also in the average. So average value of the cross section times velocity we have to consider. Now, if you consider that fusion cross section, okay. So this fusion cross section, that is sigma, which depends on, which mainly depends on that barrier penetration probability, and also, so in this case, barrier penetration probability is nothing but a raised to minus 2g, and g, this 2g is nothing but that z1 z2 is square by 4 pi epsilon 0 times that 2 pi by h cross v. This we already discussed. That potential barrier crossing probability, that is the barrier penetration probability. So that fusion cross section depends on that. And second one is that it also depends on that velocity as 1 by v square. Okay. So what it means that actually fusion cross section means if you are having that nucleus here, first nucleus here, another nucleus here. Okay. So these are the initial nuclei that are the reactant nuclei, and those nuclei combines together. So this nuclei has to move very close to this. So what is that region, minimum area that is that by which this nuclei has to be in around that second nuclei? Okay, so the area around that second nuclei where the nuclear fusion can happen, that is the fusion cross section area, or simply fusion cross section. Okay, so this is area. So if it depends on that penetration probability, that means that the potential barrier is there. So the probability to cross that potential barrier depends on your this sigma depends on that potential barrier crossing probability. If it can cross that potential barrier, that probability, if it is high, then the cross section this is larger, which means that the probability is higher. Fusion cross section will be larger, means that fusion can happen. In other words, if you consider that velocity, if these nuclei are moving with high velocity, then the fusion cross section will be smaller. Okay, if this nuclei are having relative velocity which is higher, then this cross section will be smaller, so that this nuclei has to come very close to each other, then only this nuclear fusion will happen. So the fusion cross section is an important parameter. So fusion cross section depends on this penetration probability and the relative velocity of those nuclei. So that is this fusion cross section depends on your reaction rate, fusion reaction rate also. So if you want to calculate that average value of sigma v, then first we have to consider, so what is this value that we have to calculate? So first we have to consider the particles with velocity in between v and dv, that we already discussed that Maxwell distribution. So this is given by 2 by pi raised to 1 by 2 m by kt all raised to 3 by 2, and then we have that v square term, then e raised to minus half k, sorry, mv square by kt. So this is that Maxwell distribution for that velocity. And if you consider that for particles, okay, particles with velocity between V and V plus dV. So that will be like this. And if you want to calculate that average value of sigma V, then I have to consider 0 to infinity, integral 0 to infinity. First, we have to consider sigma. Sigma depends on that probability, barrier penetration probability. And so I will take the constants as C, and then we have that t raised to 3 by 2 from here, t raised to 3 by 2, m 2 by pi or less 1 by 2, all those things will come in this constant C, and t raised to 3 by 2 I have taken. Then it also depends on that v square, that sigma depends on 1 by v square, I already told that, and that penetration v square by 4 pi epsilon 0, this is to pi by h cross v, right? Penetration probability, barrier penetration probability. So I have written only up to this. So remaining thing will be V times that probability of particles in between V and dV. So that will come as e raised to V square will come first, then e raised to minus half mv square divided by kt times dV. Now I can cancel this two. This two I can cancel. And then I will rearrange this equation by E equal to half mv square. Then you can write dE equal to mv dV, because 2 will come here, 2 will get cancelled. Then I can write this dV equal to dE by mv. So if you substitute those values here, then here sigma v will be integral 0 to infinity. I will take this m constant, that sorry, here mv, this m I will take as constant. So I will change this c to c dash raised to 3 by 2, then e raised to minus z1 z2 e square. So that I will write here this term, that will become e raised to minus z1 z2 e square divided by 4 pi epsilon 0. There is nothing changed with that, but that 2 pi by h cross v, that v will come as, from here we can see v equal to root 2e by m, root 2e by, you can derive from here v equal to root 2e by root m. So 1 by v will be root m by root v. So this is here, it will root m by root 2e. So I will take all these as constants. This much of terms I will take as constant. Okay, so that will come, this constant I am taking as a, except this minus. Okay, so that will come as minus a times a by root e, sorry, root 2e. Okay, I will take that 2 also along with that constant, right? So that will give me root 2e. Then e raised to minus e by kt, because e is now half mv square, and your dv will become dE by V, so that V and this V will get cancelled. Okay, so this will be nothing but D. So this is the expression for average value of sigma V. I can find further reduce this 0 to infinity. C dash remains t raised to 3 by 2 remains. This I can join together. So that will come as e raised to minus, let's say a by root 2e root e plus e by kt times d. So this is the average value of that sigma v. Then the probability of barrier penetration, that is e raised to minus 2g, that we applied, is only applicable for low energy. But still this equation works. Okay, so if you plot this sigma v versus that temperature, plot that sigma v, average value of sigma v in this axis. Here we have temperature. Then it will come like almost increasing initially and then starts to decrease. So at very high temperature, this average value of sigma v decreases. Okay, so that you can get from here. So when you have that sigma v, if you calculate with a different energy, okay, initially that energy, this here we have one t, here we have one t3, t raised to 3 by 2 also. Okay, so when your t is small, your average value of sigma v will be larger in that particular case. And when your t will become larger and larger, that after some limitation, so both these terms will affect with respect to t raised to 3 by 2 and as well as e raised to minus e by kt is here. So these two terms will affect for different values of t. So initially it will be like increasing. Then this when it reaches some value, then this t raised to 3 by 2 is going to act in the opposite way, because you have e raised to minus e by kt here. So when t is larger, this quantity is smaller. Okay, so minus of that quantity, so this total quantity will become larger. E raised to minus some small value will come here. So both these terms will compete each other. You can just substitute, or you can look at here. Here you can see when your t is going to be small, then you'll get minus some e by some small value here. Okay, so which means that it is approaching. So this will become e raised to minus higher value. So that is approaching to 0. So this term approaches to 0 when t is small. But when t is small, this is small. So this will increase this total value because denominator is small here. But when you are having higher t value, temperature is larger, this will become minus e by high value. In that case, this is high. This is high means this minus quantity, this will become, total will become small. So this is e to the power minus some small quantity. So this will not be dominant. This is very small quantity. But sorry, this is high. So this is high means this will become small. So compared to this will be large, because here we have this is the small one and the total will be higher. E raised to minus of that will be very small. When you take e raised to minus of one small quantity here, then it will be higher. So but at a high temperature, this term will be dominating as compared to this term. So at high temperature, this term will be decreasing the total function value, but this term will try to increase. So both these terms will act together at a particular temperature, and the resultant function will be average value of sigma v with respect to temperature will be like this. And this sigma v, average value of sigma v, depends on your rate of nuclear fusion reaction that we already discussed. That will be proportion to nx, ny, and average value of sigma v, some constant also. So that will be depending on your sigma v, means that after very high temperature, after some particular temperature value, this rate will decrease. Okay, but before that we have this rate is increasing with the temperature because of sigma v, average value of the sigma v is increasing with temperature here up to some range, and then it starts decreasing. Then that rate, nuclear fusion rate, also get decreased. So then we already discussed that for lower number of lower atomic number nuclei, we have higher chance for nuclear fusion reaction, that we already discussed with that proton-proton or proton-neutron interactions. So in that case, let's say thermonuclear reactors, thermonuclear reactors. Okay, these are the reactors which are only ongoing processes in these fusion reactions, fusion reactors. These are the only reactors, thermonuclear reactors, where you are having that temperature variation in your that plasma state, that will give you kinetic energy to this those lighter nuclei, and then which will lead to the nuclear fusion reaction. So that principle is applied in this kind of nuclear reactors, and which are called as thermonuclear reactors. So in here we have thermonuclear reactions. So in this particular case, that rate is depends on nx, ny, and sigma v. So in order to make that reactor, best reaction will be the deuteron plus triton, that is H3, which is giving helium-4, which will give you helium-4 plus 1 neutron. So this particular nuclear fusion is the best for this nuclear thermonuclear reactors. This deuteron and triton combine together and form one helium nucleus, one alpha particle, and a neutron. So here what happens is from here, what might have happened, one neutron has to come out. Okay, from here one neutron has to come out, and the remaining is combined here. One proton and one neutron is combined from each of these here and formed this helium nucleus, and that one neutron is coming out from this triton. Okay, this is the best reaction. You can also consider that H11. What happens to this case? 1 1. So in this particular case, that is proton. For proton case, what will happen? You will get two proton combining together, and you will get this one proton and one neutron. Okay, and this plus E plus, that is a positive beta decay. So that should be associated with neutrino. But this is, if you are having neutrino, then understand that this is a very weak reaction. So this is a weak reaction. Weak reaction. So since this is a weak reaction, or we can say weak interaction, weak interaction means this will happen very slowly. It will take more time. This reaction will take more time, but the fusion reaction will be happening within some few seconds. I mean, nanosecond, or very short range of time interval. Okay, even that will happen in a very short range of seconds, but this reaction will happen in some seconds, because we have that beta decay and all those things should happen. So this is a weak interaction. This will take some time to occur. So this will not contribute in that nuclear fusion process because fusion reactions will happen within that time scale that is very small. Okay. So because of that, this reaction is not favorable for that nuclear fusion reaction because this is a weak interaction and this will take more time. But the nuclear fusion reaction will happen very quickly, much less time. This will take very less time as compared to this interaction. So this is not a reaction which is appropriate for this nuclear fusion reaction. And then if you consider the deuteron and the triton reaction again, that still we need a very high temperature and confinement of those nuclei. Okay, so we need if you consider that accelerators again, accelerators. So in accelerators, we have electron acceleration. Okay, electrons are also accelerating with those nucleus in that plasma stage. We already discussed that. So when that charged particles are accelerating, they will produce some electromagnetic radiation, right? So these are charged particles, these electrons are particles, this nucleus also charged particles. So when charged particles accelerate, they produce radiation. Okay, so this radiation we call it as Bremsstrahlung radiation. Okay. Please check that this spelling again. I think I missed some H somewhere. You check this spelling. I will write it again. Yeah. Bram, radiation. So these are coming from that accelerating particles, accelerating charged particles. So these radiations are also again reducing energy. Okay, this radiation which are coming out without the nuclear fusion process. So this energy that is radiating out is taken from that accelerator energy. Okay, so that we have to consider. Then this loss will be proportional to that NNEZ square. Okay, this loss from Bremsstrahlung radiation, this is a loss. So this loss is proportional to the density of those ions, positive ions, or what we can call that nucleus, density of nucleus or positive ions, where you do not have that electrons that is in plasma state. So then you have that electron density that is also contributing this radiation times that Z square times kT raised to 1/2. So this is per unit volume per unit time. This much of energy loss will be there. So that loss we have to consider. So for energy from fusion, energy from fusion per unit volume per unit time we consider, that will be that nx ny times sigma v times q, and where q is the energy energy per reaction. So if one particular reaction happens, one nuclear fusion reaction happens, q energy will be released. So if nx ny sigma v term, if this much of reactions happens, this is nothing but that rate of reaction. So that will be this much rate, this much of reactions happening per unit time, nx ny into sigma v. Then that much times q, that will be the energy per unit time per unit volume of sample. Okay, so I think I have given some constant in that rate before, so you can, this is not required here. Okay, keep it in mind. Okay, so when you consider that Bremsstrahlung radiation, that is a loss, and the energy produced per unit volume per unit time through that fusion reaction will be nx and y sigma v, average value of sigma v times q, where q is the energy per radiation. So this much of reaction, so energy per reaction. So if this much of reactions happening in unit time, then this much of number times that rate times q will be the energy produced from fusion per unit volume per unit time. Okay. Now, if you consider that Bremsstrahlung radiation, you can see that figure here. This just so here you can see this is in energy. This y-axis, this is in energy. This is energy. Okay. And this is KT. KT means nothing but that temperature variation. So this is also energy. So this is the energy. It is might not be visible for you. So this is energy per volume that we have to consider. This is the temperature dependent, that kinetic energy of those lighter nuclei that we have to consider. So this is the Bremsstrahlung loss. This dotted line you can see from here. Bremsstrahlung radiation energy, and if you consider that DT reaction, D plus T, deuteron and triton reaction, that will give you energy like this. That energy fusion, if fusion happens, that will give you energy like this. So this is that energy axis. So with this much of temperature, kinetic energy, and if you consider DD reaction, that is deuteron-deuteron reaction, nuclear fusion reaction, then it is given by this curve, this particular curve. Okay. So while observing these two curves, we can see that the DT reaction will give you more energy. Let's say this point you can see almost in between 10⁵ and 10⁶. This much of energy it can give you. This is an arbitrary unit. Okay, so just compare these two. Okay, so don't take this as a very large energy. So comparing these two, this is arbitrary unit. So 10⁵ in as compared to this. So this is in the Bremsstrahlung loss is starting around 10⁵. So when you consider D plus T, it is having energy which is more than that Bremsstrahlung loss. So that is somewhere in this range, in between 10 and 10 1 and 10 kilo electron volt of that kinetic energy kT. Okay, so this much of temperature is enough. K is constant. So temperature, if you increase up to only this, you can cross this Bremsstrahlung laws and you can get enough energy output. Okay, but when you consider D plus T, you have you need this much of temperature, that KT value, this much of KT value, that is temperature is high in this case. Then only you can cross that Bremsstrahlung laws, which means that after that Bremsstrahlung laws, we have this output energy. So which means that in conclusion, I can say like this: if you are having that plasma state, it is having that electron and nucleus. These electrons and nucleus which are accelerating, or we can say that the positive ions and electrons that will be accelerating in that plasma state. In that plasma state, then it will produce radiation, because these are the charged particles accelerating, that will produce radiation. So whatever energy which is produced by using that plasma state, that should be more than this loss. Okay, because we have already Bremsstrahlung laws here, and then if the fusion if fusion reaction produces energy which is less than that of energy, then we will not get any gain by doing such kind of nuclear fusion reaction. So the nuclear fusion reaction should produce energy which will overcome this Bremsstrahlung laws. Then only we can have some gain, okay, through that nuclear fusion reaction. So if you consider in that scenario, if you consider D plus T reaction and D plus D reaction, that is deuteron and triton reaction and the deuteron-deuteron reaction. Deuteron and triton reaction will give you more energy than the Bremsstrahlung laws, even in this smaller temperature as compared to D plus T, D plus D reaction. Okay, so better is to use D plus T, because we need only we need a small temperature as compared to other reactions for D plus T to overcome this Bremsstrahlung loss. Okay, then only we get some gain in energy. So it has to reach at least this, and whatever energy which is coming after this. For example, if your temperature is at this point, you will get this much of energy output. Okay, this much of energy is already used for as this Bremsstrahlung radiation. So that much of energy we are already lost. So that has to be overcome first. That is overcome here. That has overcome here, because that fusion reaction will provide this much of energy, and whatever that energy which is after this Bremsstrahlung loss, that is the energy that will get outside output. Okay, extra energy we'll get. Then only that is some gain for your nuclear fusion reactor. So best is using deuteron and triton. So at lower temperature, loss is larger than the production energy. From here we can see that, and it can be observed that D plus T reaction can provide more energy at a lower temperature. So the plasma, if plasma is confined at a high temperature, it can produce energy, but in order to make this high temperature, we require energy. Okay, so if you want to increase this temperature and further this much of range, then we need more different machines, different electronic components, all those things, extra. So which require more energy input. Okay, so if you want to increase the temperature, you have to provide more energy to the system first. Okay, then that fusion, after fusion, the energy produced should overcome all this energy that is already supplied in the to that nuclear reactor to make that sufficient temperature. So this confinement uh, is maintained normally. This confinement is maintained normally for a second or a very small time scale. For a second only, we can have that confinement of this nucleus and electrons which are separated and in the plasma state. All those things will be in a fraction of second, okay, or maybe a second for a second of time scale. Hmm. So for that time, how much energy it provides through that, and how much energy we have to provide to the system, and how much energy it will give after fusion, that has to be considered. So now if you consider that number of nuclei per unit volume, that is n, if n equal to, if n is the number of nuclei per unit volume, or I will say that per volume, whatever volume we are considering. So that is n, number of nuclei per volume. And if you consider n again, how many number of nuclei, that will be same for electron also. So this is number of electrons per volume that we have taken. So both will be same because the electrons are knocked out from these atoms, same atoms we are having that nuclei. So the number will be same. Then if the temperature rise if the temperature rise by that is, if the temperature rise is capital T, let's take. So the energy given will be nothing but 3 by 2 nkt, or 3 by 2 RT you can take. This much of energy has been provided to the system. If you consider this much of number of nuclei or number of electrons, then 3 by 2 kT is the average energy. So n number of electrons or n number of nuclei are there. So n times 3 by 2 kT is the total energy which is provided to the system. Okay. And then you have that energy which is from that fusion. So I will write it as energy produced. Okay. That energy produced will be equal to nx times ny times average value of sigma v times q. That is per unit time. Okay, per unit time. So if you have tau seconds, or tau is the time, this is nothing but the confinement time. Confinement time. Confinement time means that how much time that plasma state will be there. Okay, that electron and nuclei with that much of kinetic energy is there in that your system. How much time, the time interval, how much time it will be there as in a plasma state. That is the confinement time. Okay, only that time we can have this nuclear fusion reaction. So all these process, increasing temperature, all those things will happen within that time, and the nuclear fusion also should happen within that time frame. Okay, so this is the confinement time. So this is, suppose this is some seconds. Okay, 1 second, 2 second or something. This that is a very large scale. So in that case, you have this much of reaction rate is happening per unit time. That is multiplied with energy per unit reaction. So this is the total energy of reactions which will happening at the unit time, and that is multiplied with the confinement time. That is the time available for that nuclear fusion reaction. So this is the total energy which will be produced. Now, in order to have the beneficial nuclear fission process, okay, the condition will be like, let's say nx equal to ny in this particular case. Let's say nx equal to ny equal to n nx equal to ny, that is equal to n by 2, let's say. So the condition will be, that means that the beneficial nuclear fusion condition, that will be 3 by 2 nkt. 3 by 2 nkt, that is the energy provided, must be less than or equal to, okay, this must be less than or equal to, if you put nx and ny equal here, then I will write this as n square by 4 times average value of sigma v times q times tau. So this is the condition. Now you can cancel one n here. Now n into tau will be equal to 12 kt divided by, so this is n into tau will be equal to, will 3 4 will take here, so 12 kt by, we have that average value of sigma v here, times q. So sorry, I did one mistake here. This is 3 nkt here. This 3 nkt, that is energy if the temperature rise by T, and the energy given to the system will be 3 nkt. If you are having n number of particles, n number of nuclei or electrons, then energy given to those nuclei, that will be 3 nkt. Okay, in 3 dimension, kt energy has been provided. So 3 nkt is the total energy given, and then this will come as this 2 will not be there. So this equation will be like this. So this is the condition. So this will be less than, okay, less than or equal to this. So this condition, which is called as Lawson condition, Lawson condition or Lawson criteria for nuclear fusion. So what this means? It means that whatever energy which we provided, comparing to that, the energy released or energy produced through nuclear fusion reaction must be larger. Okay, that is this condition. So that is that can be obtained by using this condition, that the energy, sorry, the concentration of that nuclei, number of nuclei per unit volume that we have given here, that into that confinement time, that should be less than or equal to 12 kt by average value of sigma v times q. Then only we will get some beneficial energy from the nuclear fusion process. If this condition is not valid, then we will be providing more energy to the system to make the temperature to make it uh, in the fusion range. Okay, that temperature we are increasing, so we are providing energy for that, but that energy will not be given back by that fusion reaction, so we will get some loss of energy actually. So if this condition is not valid, then the energy that produced will be less than whatever energy will be given to the nuclear reactor for all other confinement and other processes. Okay, so we'll wind up here and we'll continue from here in